Okay, so this part we'll talk about the phasor method to solve for RLC circuit. Phasor. So actually, phasor is used for finding the sinusoidal steady state of RLC circuit. Actually, if it is not a linear circuit, it will be possible to linearize it, but this is out of the scope of this part. But generally, it can be used for finding the steady state response. Because as you would like to solve for a ODE, then you will have a homogeneous solution. Or it is known as natural response, as I mentioned last time. Natural response. And also the particular solution, which is known as the forced response. For sinusoidal steady state, we mainly consider the particular solution because it's actually related to the sources. And for this part, as long as your circuit is stable, then usually your homogeneous solution will tend to maybe I call it x of t will become 0 as t tends to infinity, or t is sufficiently large. Usually the term of the homogeneous solution will be something like a times exponential to minus at cosine bt, something like this, or maybe a exponential to minus at, doesn't matter, or even it may be something like this. And as long as you have learned the calculus, you have learned how to calculate the limit as t tends to infinity, all these functions will become 0. All these functions will become 0. X may be something like this, then xt will be 0. And usually for the stable system, it will look like this. And as long as it has only independent source and also RLC, then the circuit is usually stable. Or this type we'll call it marginally stable if you will learn the control theory later. But it still tends to 0. Okay, so let's see. So actually, we will talk about the phasor. So let's summarize a bit. What a phasor for the sources or the RLC component. So actually, the first is RLC. So for resistance, R. For example, it is a 10 ohm resistor. Then the phasor for resistance is nothing but R, which means in this case it is 10 ohm. For this case, Next one is inductor. L. Suppose it is 10 Henry. Maybe it's too large, but just for example. And if this circuit is operate at F equals to let's say 1 kilohertz, then the phasor will be ZL equals J omega L. J is of course square root of 1. So in this case, it will be J 2 pi, and 1K is 10 to the third power, and times 10 is the inductance. So this is the phasor or the impedance for an inductor. So if the frequency of the source are different, then the impedance also change with respect to the operating frequency. And the third component is a capacitor. Suppose it is a 10 femto, also F is 1 kilohertz. Then the phasor of a capacitance will be always 1 over J omega C. 1 over J omega C. So in this case, it will be 1 over J 2 pi times 10 to the third power, and this is 10 femto. So this is the impedance of a capacitor. So for our RLC circuit, we can make this conversion. And next, as long as we may have voltage source. So if it is source something like let's see. For example, if it is a source like 20 cosine 40 minus 15 degree, then of course it is a voltage source. Then in the phasor domain, we make the conversion like 20 minus 15 degree, and actually this is the polar form. As long as I suppose you have learned the complex number. Complex number can be represented like Z equals A plus JB. So A is the real part, B is the imaginary part. Then it can be written as R theta. So in this case, R equals to A squared plus B squared, and take the square root. And actually, tangent theta will be B over A. Usually for the textbook, it will be written as theta equals arctangent b over a, but actually it is not correct. It is not exactly correct, I think. It may be arctangent b over a plus pi plus pi, or something like that. Because the period of tangent function is pi, so suppose, for example, let us draw this is A, this is B. So if you have a point here, this is point here, this is A, this is B, or if it is, maybe I should write it like this. So this is A, this is B, and this is minus A, this is minus B. So let us as C1 is A plus JB, and this is Z2. Z2 equals minus A minus JB. Then actually, this theta, because A and B are positive values, so no problem, arctangent B over A. But for this case, you see that tangent theta is minus B over minus A, which is B over A. So they should be the same, but in this case, theta should be arctangent B over A plus pi. Should be something like this. Should be because arctangent usually gives the value from maybe 0 to pi or minus pi over 2 to pi. If it is 0 to pi, then you need to add the pi, which is determined by the sign of the imaginary part. For example, in this case, if your arctangent give your range, give the range 0 to pi, then if B is negative, then you need to add the pi so that you got the correct theta. And actually this is the case for first quadrant and the third quadrant. And for the second and fourth quadrant, it will be similar. But and also it depends on whether the range of the arctangent gives you the 0 to pi or minus pi over 2 to pi. Then you need to be careful about that. So actually, for the complex number, we have the rectangular form, and this one is the polar form. This is a polar form. Or sometimes z equals r theta can be written as r exponential to j theta, and actually e to the j theta equals cosine theta plus j psi theta, which is known as the Euler's formula. So actually, this one and that one are actually the same. It has r and theta. So let's see an example. Let's see an example. Okay, so we have a circuit like this, 20 cosine 40 minus 15 degree. So this is a voltage source, and this is a 60 ohm resistor and a capacitor, 10 millifarad, and the inductor is 5 Henry. Okay, and this is VO, this is VO. So here determine the steady state response of VO. Determine the steady state response for VO. So actually we use the phasor technique, then we can convert the voltage source like this, and then for the resistor it is still 60 ohm, and for the capacitor we know that in this case omega equals 4, and actually omega equals 2 pi f. So actually here we can see that the C should be, this C should be 1 over J, omega is 4, and multiply C 10 times 10 to the minus 3 power. And actually this is minus J25, so minus J25. And for the inductor, here it is J omega L, J4 5. So J omega L. And in this case, this should be J20, and this is the phasor for the V out. So this is the phasor conversion, and this is supposed to be the step 1. You convert the circuit in the phasor, domain. So next, we can simply calculate this circuit. Just imagine all like resistor, but the resistance for this element is an imaginary number, and also for this. So so actually for this one we calculated minus J25 parallel with J20. Yeah, it would be minus J25 J20 minus J25 plus J20. So in the denominator minus J5, and in the numerator j square will be -1, and then we have another minus sign, so it is positive. And then 25 times 20 will be 500. So the answer will be J500. J500. Okay, J500. No, J100. J100. Okay, so so this is the parallel impedance, and in this case we can write it like this. So 60 ohm, and then this part is this one is J100. J100. It is not necessary to be a real, purely real value or purely imaginary value, but at this time it is purely imaginary. But generally you can show a box to stand for that equivalent impedance. So and for this case, VR is still this 2 point, because VR is the cross voltage, or this the voltage difference between this point and that point. So you can regard it as this point and that point, which means that VR is the voltage difference between these 2 points. And in this case, you can write VR to be 20 minus 15 times J100, 60 plus J100. So can have some simple calculation. So it will be 20 minus 15, and the latter one, you can calculate it to be, so actually we can just, so we can make some calculation. It will be J10, 6 plus J10, and then we multiply it by 6 minus J10, 6 minus J10. Then the denominator will be six squared is 36, so 136, and on top it will be 100 minus 100 minus 60, J60, plus J60, plus J60, plus J60. And you can find that for this complex number, you can convert it into the polar form. So that you calculate by 100 square plus 60 square. So you convert it like this: 100 square plus 60 square, take the square root, over 130. And this one, the angle would be arctangent 60 over 100. 60 over 100. So in this case, 60 square plus 100 square, take the square root, will be 116. and then divided by 136. So this will be, or maybe I can directly write it here. So it will be 0.857, and then the angle will be 60 over 100, and then arctangent. So radian is 0.54, and if we use the degree, so you multiply it by 180 and then divide it by pi. So it is 30.9 degree, and we know that this is positive, so it should be in the first quadrant. So in this case, this should be minus 50, and as you know that for complex number, in the polar form, it is easier to calculate the multiplication. So that 20 multiply 0.857, it will be 17.15, and then for the degree, it will be you add them together, 30.9 minus 15, so it will be 15.9 degree. So this is the phasor for V out. So in the time domain, so here for step 2, so this is step 2. Step 2 is to solve the circuit in the phasor domain, and then finally it is step 3. You get the answer in the phasor domain and then convert it back to the time domain. So you see that the answer is this one, and then VOT will be 17.15. Not enough space. Cosine. So originally it is omega equals to 4t. So here we have 40. The degree is 15.9 degree, so plus 15.9 degree. So, and this is done. This is step 3, convert it back to the time domain. Or maybe it's more accurate to write it as a 16.0, but it doesn't really matter. Okay, so this is a simple example about the usage of the phasor technique. So let's see another one. Okay. So let's see an example. Okay. So here the circuit is already converted into the phasor domain. So here this is a current source. This is a capacitor. And minus J3 ohm. And this is 4 ohm. This is plus minus 10 45 degree 10 45 degree volt. This is A. So next, an inductor, J6 ohm. This is 12 ohm. And this is V1, this is V2, this is V2. So usually in the time domain, we'll use the small letter. Time domain, we'll use the small letter. For example, V1, V1t for the time domain. In the phasor domain, we'll write it in the capital letter. But it is only a complex number. This is a real sinusoidal function. And usually a single frequency. Otherwise, if it has a multiple frequency, you need to separate into many cases and then add them together. Okay, so in this question, you're supposed to find V1 and V2. V1 and V2. So the circuit is already converted into the phasor domain, so it will be easy to. We can just skip the first step. So for node 1, we can node 1 we can write the nodal equation. So 3 0 degree is going in, and actually this is a voltage source, so that we don't really know the current going through this. So actually we can regard it as a supernode. So actually we can regard this is a supernode. So so the first current, this is going in, this is going out. So this one will be V1 over minus J3, and then this one is going out, so we have a V2 over J6, and then this one is going out, so that we have V2 over 12, and so this is not actually not the no equation, and no one actually for the supernode, and within the supernode itself, we know that V1 is V2 plus tan 45 degree, so that we can write V1 equals V2 plus tan 45 degree. And in this case, we can just substitute V1 into here, so that we have so 0 degree is actually 3, and then V1 is V2 plus tan 45 degree is actually tan 45 degree is actually 5 square root of 2. Or 707 plus J707, and then over J3 plus V2 this one also need to divided by minus J3, so second term and the third term, nothing like this. So this is a complex number, and then so that we can move it to the left hand side, and then we add this one together, so that finally we can find that V2 would be 31.41 minus 87.18 degree volt. So this is V2. Supposed to find. And the next one we would like to find V1, which will be V2 plus 1045 degree. So it will be 25.78 minus 70.48 degree, also in volt. So actually for this question, the phasor is already the answer, but if you like to convert it back to the time domain, actually V2 will be something like 31.41 cosine. Actually, we don't really know the frequency, so we can only write omega t minus 87.18 degree. It's not mentioned in this question. And V1 will be in volt. Ouch. Volts. So V1 will be 25.78 cosine omega t minus 70.48 degree, also in volt. Okay. So let's see another example. Okay. So 8.3. Okay, so it could look like this. Yeah, 50 degree, and this one is a capacitor minus J2 ohm. This is 4 ohm. Ouch. J10 ohm. I3. This is 8 ohm. This is minus J2 ohm also. And here is voltage source, which is 90 degree volts. 90 degree volt. So in this question, you're supposed to determine I/O. Determine I/O. But in this one, we may try to use the mesh analysis. So this is I1, this is I2. No, this is I3. This is I3, this is I1. This is I2. This is I2. Or in clockwise direction. So we may try to write the mesh equation. So first of all, for mesh 1, which means I1 loop, mesh 1. So we have 8 I1 plus J10 I1 minus I3, because I3 going this way. So for this inductor, I1 is a positive direction, I3 is the negative direction. So we have a J10 multiplied by I1 minus I3. And for this one, minus J2 is this capacitor. So it will be I1 minus I2. So this is the first mesh equation. And actually we can simplify it a bit so that we have I1 8 J10 minus J2. So we have 8 plus J8, okay, and for I2 only this one multiplied by minus 1, so we have plus J2 plus J2. And for I3 the right hand side will be equal to 0, so we have only this one. So it will be minus J10. So this is the first mesh equation. And then for the second one, mesh 2. So first we have this minus J2, and then the current I2 will be positive, and then I1 will be negative. Next, also this one, minus J2 multiplied by I2 minus I3. So minus J2, I2 minus I3. And then next, 4 ohm multiplied by I2 plus 4 I2. And then finally, this is something like a voltage drop for this loop, because this point is high voltage, this is a negative point. So we have plus 20 90 degree equals 0. So this is the second mesh equation, and then similarly we can simplify it a bit. So we have I1, so it will be J2 I1. And then for I2 we have this one minus J2 again plus 4. So it will be J minus J4 I2. And then for the I3, only this one. So plus J2 I3. And this one, we move it to the right hand side. So 90 degree is 90 degree is actually J. So 20J, and then we move it to the right hand side, so minus 20J or minus J20. And so this is the so we have first equation, second equation. And then for the third loop, actually I3 is nothing but 5. So for mesh 3, we know that I3 is nothing but 5. 0 degree, which is 5. So finally, you can just substitute I3 to be 5 here and here. Then you can come up with two equations with two unknown. Two equations with two unknown. Then actually you can further simplify it into 8 plus J8 I1 plus J2 I2, and then I3 is 5, so equals J50. So this is 1 prime. For the second equation, you have J2 I1 plus 4 minus J4 I2. So this one is 5. 5 times 2 is 10. So with the right hand side is minus 10J and minus 20J. So totally minus J30. So this is the second equation. So now we come up with two equations with two unknown. So or you can actually rewrite it like this: A plus J8 J2 4 minus J4, and this is I1 I2 equals J50 minus J30. So you can use the method in high school, in high school to solve for this one. You can multiply, for example, multiply the first prime equation by 4 minus J4, and then multiply by the second one by J2, and then you subtract them. Then you can eliminate I2, then you find I1, and then you substitute I1 here, then you can find I2. Or actually you can use the linear algebra, something like A, B, C, D, X, Y equals EF. Then X, Y will be nothing but A, B, C, D inverse EF. And A, B, C, D inverse is actually AD minus BC, and then this is actually D, A minus B minus C, EF. And it will turn out to be AD minus BC, and then DE minus BF, and then here we have AF minus EC. So this is the linear algebra method. So if we use this one, we can know that I1, I2 will be A plus J8, 4 minus J4, and then D is this one. Which means 4 minus J4. E is this one, J50, and then minus B is J2, F is minus J30. A is A plus J8, F is J minus J30, and then minus C is J2, E is J50. Let me see if it is correct. J50, J2. Yeah, think so. So finally, you will find that I2 would be 6.12 minus 35.22 degree. And for the upper one, let me see. Well, actually, I1 is not really important, but we're supposed to find. Actually, we're supposed to find I0. I0 is actually minus I0 is actually minus I2. So this is a number, but actually we don't really need to calculate about it. And the final answer, I0 will be minus I2, which is 6.12 and 144.78 degree A. So this is the answer. Although I know that this is negative, but do not write minus 6.12, 35.22 degree. This is incorrect. This number must be positive. Must be positive. So let's have a break, and then we'll have some more example.